This is our work about tampered text detection in photograph documents. First is about the background of this work. The three most commonly used document image tampering methods are copy move splicing generation. Copy move means shifting the spatial locations of texts within images. Splicing means copying text regions from one image and paste to other images. Generation means replacing regions of images with visually plausible but different contents. Comparing to manipulation on images, document tampering has two main features. First, the area of tampered text are small. Second, less likely to leave visual tampering clues. The motivation of this work is, in the aspect of data, there lack a public dataset that have enough samples and close enough to real-world scenarios. In the aspect of method, previous methods can't effectively detect document tampering that lack visual tampering clues. Then about the DocTamper dataset. The proposed selective tampering generation is to reduce the annotation costs and mimic manual tampering process. The pipeline of it is shown in this figure. The core concept of it is using sizes, foreground, and background statistics of texts to approximate font information that cannot be directly obtained from complex photograph documents in complex scenarios. Tampering text with similar style, foreground, and background color and texture to reduce font and position distortion. We collect 50,562 images of contracts, notifications, receipts, invoices, sheets, notes and pages from various scenarios and build DocTamper dataset to address the lack of sufficient data that can reflect real-world demands. Some basic statistics of the DocTamper dataset are shown there. The main features of DocTamper dataset are summarized as: first, large scale. The public datasets in previous works only have less than 1,000 images, while DocTamper has total 170,000 of images. Second, board diversity. To build the DocTamper dataset, we collect document images from various publicly available websites and document image datasets. Various bilingual real-world document images including contracts, invoices, receipts, etc., are included in the source images of our dataset. Third, comprehensiveness. All the three commonly used text tampering methods are included in our dataset to imitate the real-world applications. In addition, we introduce two cross-domain testing subsets to fully evaluate the generalization ability of different methods. Then about the document tampering detector. The proposed DTD can detect the tampered texts that have seldom visual tampering clues, since the tampering operation can cause the discontinues of block artifacts grid. The overall framework of the DTD are shown in the figure above. It extracts visual features through visual perception heads and extracts frequency features through frequency perception head, then fuse them in an early fusion manner before fed them into multimodality transformer. Finally, a multi-view iterative decoder is utilized to get the predictions with the multimodal features. Here are some theoretical analysis about why DTD can detect tampered text without visual clues and why it has strong generalization ability. First is about what is block artifacts grid. The photographed document images will undergo slight lossy compression on almost any device after being captured. Currently, most lossy compression of images will generate block effects. Taking the most common JPEG image as an example, it independently quantize each image block in the Y channel in the frequency domain after imaging to remove high-frequency components and reduce storage occupation, as shown in the following figure. The independent frequency domain quantization of blocks will cause the numerical characteristics of the DCT coefficient matrix of the image to exhibit periodic changes of 8 cycles, presenting a grid-like distribution, which is known as the block artifacts grid. Tampering operations typically disrupt the continuity of the block artifacts grid, resulting in fracture of the block artifacts grid at the edge of the tampered area and abnormal distribution of DCT coefficients within the tampered area. Although careful document image tampering is difficult to capture at the visual domain, if frequency domain input is processed in an appropriate way, local anomalies in the block artifacts grid can help locate the tampered area. On the other hand, various types of tampering can lead to discontinuity and distribution anomalies in the block artifacts grid, which can be captured through appropriate methods. Being able to unify different types of tampering methods into an approximate pattern is beneficial for helping the model achieve stronger generalization. Then about the proposed frequency perception head. The motivation is to assist in locating tampered text that have seldom visual traces by capturing abnormal in block artifacts grid. The core concepts are: encode the discrete DCT coefficients with orthogonal basis embedding to sensitively capture local anomalies in BAG, automatically learn the optimal features under different compression settings through learnable quantization table embedding, downsampling with a convolutional layer of kernel size 8 to align the period of the BAG and aligning visual features through position encoding. Then about the proposed multi-view iterative decoder. The motivation is to mimic the process people zoom in and out the image over and over again, combining clues of different views and analysis them repeatedly to do careful tampering detection. The core concept is alternately fuse high-level semantic information and low-level detail in vertical direction, and continuously refine the features in horizontal direction. Ablation experiments shows the effectiveness of each proposed modules. Comparison experiments shows that the proposed method outperforms previous methods. Here are some visualization results. Thank you very much.